First, we'll go over an overview of what the AMS tool is all about. The AMS tool has four important aspects. It's integrated with DX Designer, so the interface should be fairly familiar to most of you. And we've worked to simplify the design process within that environment. Next, we have a pretty large model library and support a lot of different types of models. So as you can see, there's VHDL-AMS, SPICE, C++, and Verilog. Which really opens up the door to a lot of different types of simulation capabilities. Not only analog and digital, but things like hydraulics, magnetics. AMS comes with a very powerful post-simulation analysis tool for viewing your waveforms and manipulating them to get the measurements and information that you need. There are also tools that can help you build your own models if existing models don't exist. Alright, let's go look at the tool now. So here we are in Xpedition Designer. It's a PCB schematic. As you can see, it's the same icons that you're familiar with. We do have some extra stuff in here. If we go to Setup Settings, you can see under Licensing we've turned on AMS, and that is added in this additional toolbar, which gives us access to various simulation functions. We also have under the Navigator a simulation tab, and this will get us access to information about the simulation as well as some of the SPICE model data. So at this point we are pointing to our PCB library, and we've got our PCB parts with this cell data in there. Chances are that your library, most libraries set up for PCB, are not all also set up for simulation. They can be. We support that. It's just a matter of adding some additional properties, but in the case that they're not there, there's a couple things that we can do to help easily deal with that. One thing, if you want to use some of our simulation models and pull from there and do some simulations, come up here under Simulation Settings. There's an option to switch central libraries, and this will switch to a library that is specifically set up just for simulation but not for PCB, and you can use that to analyze your design. The other thing that's going to come up is the fact that a lot of these parts need additional properties, as I mentioned. Things to identify what type it is to the simulator. That's what the prefix property does. Identifying where the simulation value is going to come from. That's what the order property is doing here. It's saying pull the value from the value property there. So, but I need to get those properties added on, but I don't have to do that manually. I don't really even have to think about that. We'll just come up here to Simulation and come down here to Simulation Data, and we can click on Update Schematic. And what that's going to do, it's going to go ahead and look at all the parts in the design and try and identify what type of part it is. So in the case of a resistor, it'll see that the reference designator is R, so it knows it's a resistor, and it'll add all the appropriate properties for that. So that'll take care of like 90% of the design, all the resistors, capacitors, inductors. You can add in additional modeling information to get more complex parts. So that will take care of setting up parts for simulation. There will be other parts that are not set up. So if we come up here to Simulation and then Set Up Schematic, we can see a list of all the parts on the board and see which ones have models. In this case I have models for all of those, but if there are any that we need to update or add to, we can go ahead and check those and do Edit Assign Models. And then we can choose what type of model we're choosing. Let's say it's a SPICE model. We can pull models from our library, or if you have models that you pull down from the internet, we can point to those. If the models are PSpice formatted, we can change the syntax so that it works for our simulation tool. Once you've gone ahead and identified what type of part it is that you're working off of, we can go ahead to the next part where we're mapping up the ports in the model. So you can see down here, sub-circuit line. These are the ports that we need to hook up to the rest of the design, and we will link them by the names of the pins on the symbol. So we can see a nice definition of what's going on here. We can change around which ones are which here. So let's say pin 2 is our positive input, and then negative input is number 3. Then we got our output coming there. We got our power supplies, and then that defines how we're hooking the model up there. And then if there's any additional properties, we can set them up at this point. Anyway, that will take care of the more complex parts, so we can just work through the list that way. Once we've done that, this design is almost ready to simulate. We just need to set up some sources. There's a couple different ways we can do that. Again, if we've switched over to our simulation library, we'll have access to voltage sources, signal sources, whatever we need. If we want to stay within our own library and we don't want to mess up the schematic by adding some test bench parts, then we have the option to just select parts like this VCC right here, right click on this and say add source, and we can say this is going to be a voltage positive 5 VCC and DC, so we'll define this as 5 volts. And then if we're doing any frequency analysis, we could add in a value for that. But this will add in that voltage source in the background, connecting it to these two nodes. And I don't have to see that on my schematic. It doesn't mess up things graphically, but it will be part of the simulation. There's also the ability to add in other sources like pulses, sine waves, lots of different things here. We've got some digital and other electrical sources. So you just define what you want and which pins that you want to hook that up to, and then you'll be ready to go. All right, let's take a minute to talk about model support with Xpedition AMS. I've switched to a different schematic that's more deeply focused on simulation. You can see we've got some test bench items in here. There's a large number of other items in here that are of interest in the model space. So right off, this op-amp is using a SPICE model. That's kind of what we've been talking about. But we also have the ability to integrate into the simulation VHDL-AMS modeling. So for example, this part right here isn't actually a PCB part. It's not going to be part of the end design. It's a simulation part which is using a VHDL model to figure out the heat based on the power that's going through this transistor. So this op-amp's driving this transistor, and this part's just kind of monitoring the current and the voltage on that part. We'll go ahead and push into this just to see how that's working. You can see it's a VHDL formatted file, but down here is the heart of it, the model information here. We're multiplying the voltage times the current and turning that into the heat flow. So we go back to the schematic here. This pin right here coming off of that is going to be a heat value. Comes down here to a thermal capacitor and a thermal resistor. This is going to represent the heat sink on the board, and that transistor is going to be hooked up to that. We can see there's also another net hooked up to this. So this is this resistor, which is also using a VHDL model to do that modeling. And that information comes off of here. It goes through a thermal to digital converter to an additional VHDL block. This one is just straight logic. It's going to just take the value of this, whether it's a 1 or a 0. If the temperature is too high, it'll be a 1, and it'll go ahead and use that information to shut off the switch, which will turn off this amplifier. So you can see that VHDL functionality there adds in the ability to really expand what you're simulating here, getting into the whole system of the design. Alright, so we come down and look at the library real quickly and look at the partitions we have available here. We've got obviously a lot of different SPICE models that are available for you. We also have some VHDL modeling, digital, electrical, hydraulic, magnetic, mixed signal, mixed technology, rotational, thermal, transitional. So lots of different things in here that you can take advantage of for the simulation. If you want to throw in a fan and model the rotation of that fan, we can do that. So if you do want to expand your simulation into this space of using some of the VHDL-AMS modelings, it's a standardized language, lots of documentation out there, but as far as getting the syntax of the file itself put together correctly, if we come up here in the simulation, there's a VHDL model wizard that will step us through the process of building that up. So we just have to work through this wizard and answer some of these questions. It just takes some basic knowledge about what the VHDL-AMS model is expecting. What are your generics? What are your ports? Any other declarations? And then you get in the architecture. The architecture is where the model is located at. But this will make sure that the code that's built up will be syntactically correct. You just have to give some guidance on what's going on. Maybe you just want to grab an existing VHDL-AMS model and work off of that. At the high end of the Xpedition AMS package, you can integrate with ModelSim and have large VHDL or Verilog blocks that you're simulating. ModelSim would obviously speed up the simulation on that end. Or you can also link up to tools like MATLAB and have part of the simulation running in MATLAB while the circuit itself is running back here in AMS. So we'll move along at this point to the simulation itself. We can kick that off either from the pull-down menu or from the toolbar. There's a little running man here that's to start the simulation. We'll click on that. That brings up the simulation control window. You can see down on the bottom it went ahead and looked to see if there was a netlist required and did some other work to prep the design while I'm defining what type of simulation I want to run here. Right now we've got it set up for a time domain analysis. There's additional settings for that. If we're working on convergence issues, we can come in here and tweak that. The easiest way is if we are having convergence problems, just to switch this over to more accurate. It'll take a little bit longer to run, but more likely get through those convergence issues, which is typical with SPICE to have convergence issues. So we can also change the integration method if we want. So there's a lot of stuff here to really help cope with those types of problems. But at this point, the simple enough design, we'll just run a time domain analysis. Frequency analysis is over here. There's the standard settings there, how many points per decade or octave or linear. And additionally, you can do some noise analysis on the frequency side. Back here on the time domain, you can enable an FTT if you want to get that output at the end as well. We've got a tab here to define which results you're going to keep. The tool is going to be simulating everything, and you just define what it's going to save off. We could just do the top level. If we're trying to do a little bit of debugging, maybe on some of the models, we might want to do all the waveforms. If we're dealing with a big, long simulation, we may want to cut that off so we only save in selected waveforms. Leave that with the top level for now. There's also some multi-run simulations. We've got sweep values, so you choose a value like a capacitor value and sweep the value there. There's a Monte Carlo. Actually, the Monte Carlo sensitivity and worst case are all going to key off of the tolerance values that are set on the parts. So Monte Carlo is going to randomly grab a value within that tolerance range and do that for all the parts that have a tolerance, and then run a simulation. And it's just trying to randomly figure out what the possible outcomes are based on the tolerance ranges you've set. Sensitivity is going to alter the values of those parts that have tolerances set by just 1%. So each part gets modified by 1% in turn, and then we come back and we can see which one had the largest effect on a particular outcome. And then worst case, it's just going to go to the extremes of that tolerance range. So we have all these available to here. I'm going to go ahead and run the sensitivity analysis just so we have those results. We'll just come back here and kick off the simulation. Now while this is running, we can monitor down here at the bottom where it's at in the simulation. There's the ability to stop the simulation if we want to, and then resume it from that point. All right, when that's done, we get the waveform tool up with our results. Now that the simulation's done, we'll go ahead and look at some of the results. We've got our currents up here at the top. Just double click on one of these. We can see the current coming in. We can also see the voltage. With this, we can put them both on the same scale, and then we can go ahead and take measurements against those. Just move this around. We can add as many cursors as we want, so that's not an issue. Just keep adding those in and measure the spots that you're interested in. You can see with these we've got several waveforms all in one place. That's because this was a sensitivity analysis, so we had 8 waveforms per measurement. Alright, so let's go ahead and look at the measurements toolbar. Go ahead and look at this. We've got lots of different options that we can use to measure a different waveform. So, anything from amplitude, bandpass, low pass, mean, medium, just pretty much all the measurements you could think of. But you go ahead and grab one like maximum there. We're going to annotate the waveform. We can choose to do that over the entire waveform, or if we've zoomed in, we can just do it on that region there. Or if we've got 2 cursors, we can measure in between those, or just define 2 x values. So we'll just go ahead and apply that, and that goes ahead and puts that measurement on the waveform. Now, since this was a sensitivity analysis, we've got some additional options here. Plot sensitivity of maximum, and let's go ahead and apply that. And what it did was it took the different simulations, and it's showing me how much each of these values affected the vsense values for the maxims that it was getting to. And it looks like in this case resistor 0 had the largest effect. Resistor 1 had the second most effect on that value. So if this was critical to me for some reason, I might want to invest in parts with lower tolerance so that I can keep those values more predictable. There's also a calculation tool, so if I were to come ahead and bring up the calculator, we could bring in the vsense, and if for some reason I wanted to, I could multiply this times the current there, enter that, and then get out it'd be a power rating if that made any sense. So we can get that across there. Alright, there's also the ability to do a post-FFT analysis on a waveform. Let's go ahead and select that one, and then hit FFT, and then we'll say OK, and then enter. And that'll go ahead and plot out our FFT of that particular signal. The waveforms can be modified, different colors, adding in additional text. And of course you can save off the waveforms, copy them to clipboard, work with them that way for documentation purposes. If for some reason you wanted to export the data out, there's always the ability to save this off as a CSV format, or you can see there's other formats. Maybe we save it off as a Mentor Graphics database and bring it back in to compare to some other simulation. Once the simulation is done, we can come back here to the schematic, and assuming there's an operating point value assessed, we can click on the back annotation of that operating point, and you can see that throughout the schematic we've got those values there. So if you're balancing a transistor or just wanted to get a good feel of how things were running in the DC state, we can do that. Also a good way to check to make sure you got your voltage supplies hooked up correctly. So we can just go ahead and turn that off again. So as you can see, it's a fairly powerful, well-rounded tool. We're integrated with the PCB schematic. Got lots of stuff to make that flow nicely, make it easy to set up a design that was originally focused on PCB to get it ready for simulation. Lots of different models that we can support. Specifically, the SPICE is used for a lot of the simulation, but for cases where models aren't available or you want to do something tricky, we got the VHDL-AMS modeling. And then at the high end, again, you can integrate with C or MATLAB. And then we've got that advanced waveform analysis tool at the end. Lots of measurements available for you, a calculator to do all sorts of calculations, and then specific multi-run type simulation analysis views like the sensitivity view. So it's a tool that can easily handle your analog functional simulation needs.